So, first, actually, let's go over here. I want to, what the heck? Okay. Okay. So, before we get into today's lesson, I want to remind you of one big idea of calculus, and that is sometimes you calculate, make a calculation from a product. For example, distance is a product of rate times time, yeah? Okay? Sometimes, however, if one of those factors varies constantly, if, for example, the rate is constantly changing, it's not always 3 meters per second, it's, you're going faster and slower, then you need to make mini calculations, right? So kind of rates times little increments of time, and then you add all of them together. Add the calculations. What calculus adds many little sums of calculations? That's a sum, yeah? See, sum starts with an S. Okay? Now then, that's a big idea of calculus. That is, in fact, half of calculus, the integral calculus. Keep that in mind as we talk about today's lesson. Now, here we go. Fluid force. Imagine a submarine. I was going to show a clip from U-571, but I just don't. It's a great movie. You should see it, but I don't have time. Imagine a submarine diving down to a depth of 500 meters. Now, the submarine is surely now feeling far more pressure per square inch than it did at the surface. Yes? Anybody done scuba diving? Okay. All right. Imagine it. Now, that's the idea of the day. Now, consider a couple more or other variables. Imagine a really big submarine and a little baby submarine at the same depth. Now, the big submarine has far more surface area. Yes? So if I'm calculating how much pressure per square inch, then which one feels more pressure altogether? The big one or the little one? Now, people say the little one because it's so little, it's feeling so much pressure. But which one has more area on which to feel pressure? The big one. The big one has more force applied to it because it has more area to feel that force. Yeah? Don't think, oh, the baby, poor baby. Okay. Last but not least, imagine a submarine dives into pudding. Okay? Does that submarine feel more pressure than it would if it was in water? Yes. Okay then. The main variables for this problem then are all what we just talked about. What are some of the variables that affect how much force something? So one is surface area. Okay. How much area there is to feel the force. What else? Depth. Yes. The greater the depth, the more pressure. The more pressure, the more force. And what else? Density, the weight density, or just the density of the fluid itself. Okay, now those are the three variables for force. Force depends on rho, that's rho, the weight density of the fluid, which is a constant. D, depth, and A, area. Right? Now, the units here, let's go, units. The units on rho are newtons per cubic meter. That's weight density, yeah? All right, so mass over volume. Depth. Depth is typically in meters in our problems, and the area is in meters squared. So all together then, when you calculate newtons over meters cubed times meters squared, you get newtons, which is force. All right, now, two totally different types of questions. Depending on if it's horizontal, which is algebra-based physics, or vertical, which is calculus. Say a cubic submarine. Yes, obviously that's crazy, but a cubic submarine with edges of 2 meters is submerged to the top of the sub rests 30 meters below the surface. So here's the surface of the water. Okay, here is a cube, and this distance to the top is 30 meters below. Here's the cube. How much force is applied to the top? We just said force is a combination of weight density, depth, and area. You'll eventually memorize this. For water, the weight density is 9,800 newtons per cubic meter. Okay? You don't have to memorize that. I'll give it to you if it's necessary on any test. So, in this case, what's the weight density? Good short-term memory, 9,800. D, that's the depth. 30 meters. And the area. It's a square face, so the area of that is 2 meters by 2 meters, or 4 square meters. Okay, so all together then, you definitely will need a calculator today. You're going to be doing it for large numbers. 9,800 times 120 is what, 98 times 12 with 3 zeros. I don't know, hundreds of thousands probably, maybe millions. 1,000,000. 172,000. 76,000 newtons. Okay? Are you with me? All right, now, in the bottom case, the rectangle is exactly the same. So why will the force on the bottom side be different?
Deeper.
Deeper, okay, so would you calculate the bottom, the force applied to the bottom? So just 2 meters deeper, so now the depth is 32. Okay, so what'd you get for the force there? Obviously, it should be more. 1,254,400 newtons. Can I just take a second to appreciate that you know place value? I have students all day say 1,254,400, which is it's like they never went to kindergarten. Okay, all right. So good deal. Now that obviously is not a calculus problem. So the question is, if you talked on a vertical face, why is calculus necessary? Why do you have to use calculus when you talk the force applied to this face? What? It's changing depth. The depth isn't the depth of this. Think of this little rectangle. Does that rectangle feel the same depth as this rectangle? No. No. So this is a case of calculus where you have a varying, constantly changing factor. Okay? The depth is constantly varying. That sounds like an oxymoron. But it's constantly changing. And so we need to make more of a calculation of force to many slices. I guess all that then is the cart before the horse. I just asked the question. So vertical is different because the horizontal, every one of these little squares has exactly the same depth. So I don't need to use calculus for that. But on the side, every one of these little areas has different depth, and so I do need to use calculus. First thing I want you to do is locate your axes. I would strongly recommend you try and exist in the first quadrant, and I think it's best to put the origin at the bottom of the container. Now, the top of the container then will be at 2, and the surface of the water will fall at 32. Are you with me? Okay, so how far is it from the bottom of the container to the top of the container?
2.
And how deep is the object? 30. So from the top of the container to the water is 30. So 2, obviously not drum scale, but 2 and 30 is 32. Yay? All right, cool. Now, if then I want to calculate the force here, then I would have to say, all right, well, what's the force at that level? And then I'd have to do another calculation of what's the force at that level, because they have totally different depths. And this level, I would have to do infinitely many of these calculations and sum of them. So it's the sum of many forces on each little slice. So when I say force is rho dA, then the A is not the area of the rectangle. I'm not talking 4. It's the area of one little slice. How many square inches or meters does that little slice have? All right? So if we get into this here, rho we could put out front because it is a constant. Actually, I'll write the formula first. 9,800. The depth. Okay, so let's start here. Depth. I think you'll agree that there is a slice at 1 meter, yeah? How deep is it? 31 meters, okay? Would you also agree there's a slice at a half meter? How deep is it? 31 and a half meters, all right? So it seems like the depth is always relative to the surface, yeah? So how are we calculating that every time? You said 31 here. How do you get 31 out of these numbers? 32 minus 1. You said the depth here was 31 and a half. How do you get 31 and a half out of these numbers? Okay, so what if the slice is at y? Okay, so the depth is 32 minus y. Y is the distance from the axis up to a slice, so the depth is 32 down to the slice. Notice it's consistent with the calculus we do on areas. It's upper minus lower. All right, now, the slice, the area of the slice. This is a rectangle, and what is the base of each rectangle slice? 2. Every one of these has a base of 2, I think you'll agree, yeah? And the height, dy, beautiful, dy. Super thin. You'll notice that these are always y-based, because it's all about how it's changing with depth, and so every one of these force problems will be y as the variable of integration, right? What are the limits of integration? 0 to 2 or 0 to 32? Or 2 to 32? 0 to 2. Why 0 to 2? You're absolutely right. Yeah, there's liquid up here, but I'm calculating where the force on the face is. There's not even face up here, so I would definitely not go up here. It's 0 to 2. You with me? All right, throw that in your calculator. That's not hard to calculate, but we're going to focus on concept. or it's not hard to integrate, rather, is what I meant to say. But we're gonna just use our calculator for these, focus on the concept. This will probably be exactly, I don't think we'll. These will be really large units, numbers usually. What do you got?
215,000.
215,000?
Yes.
1,215,200? We good? Okay, cool. Now, this is pretty basic, and it's because it had a rectangular face. Things get a little different depending on if it's a different face or half full, a couple different variations. So, depending on the case, sometimes maybe you'll get a case like this guy. If this is imagine this is a container that's filled with fluid, and we want to calculate the force on this triangular face. Obviously, it has several faces. I'll tell you, those of you going to go on with engineering or physics, that slanted face, that's a little harder to calculate the force on. But I'll let, if we get to that, great, but it's not part of what I need to do. We're going to just calculate the force on the triangular face. All right, now read carefully, okay? A trough with a right triangular face, top edge of 9, side of 4, is filled half the way up. Half the way up. That's important. Half the way up. So it's only filled to 2 with gasoline, which has less density than water. Find the force the gas exerts on the face. So I'm only trying to talk the shaded region's force. Down? Now I cannot gauge whether your integral is correct if you don't locate on your paper where the origin is. Depending on if you put the origin here, then your integral will be totally different than if somebody puts the origin here, and that person's integral will be different. The answer will be the same. Now, I can't check that you set it up correctly if I don't know what y means to you. So I have to see a picture and the origin. Now, on this, you'll see, I'll guide you for a while in where to put the origin to make your life easiest, as opposed to making your life, you could get the right answer another way, but it'll be much harder. It's much easier in this case if you put the origin at the bottom. All right? Now, I think you'll agree that, again, because it's a vertical face, each of these little slices has a different depth. And so I need to make many calculations of force and add them. So this is the ideal I will have to use, and the row I can put up front. This isn't science class, so I beg you, please don't worry about putting the units everywhere in the problem. That gets gross to me. Okay, the depth. What is the depth of each slice? Okay, so this slice, would you agree there's a slice at 1? How deep is it? Is it 1 meter deep or 3 meters deep? Okay. So say I have a pin that's out. Okay. Say I have a container that's 4 meters deep, and I want to talk about how deep this slice is. Okay. Here's the. Let's go with. Here's the top of the container is 2. Is the top of the fluid is 2. Now, say this is the container. All right. Now say the container gets really huge, so it goes up to 50. Is that slice any deeper now than it was before when it stopped out at 4? What if this container went to 1 million? Is this any deeper than it was before? No. So does the top of the container matter at all as far as the depth? No, it is all about the top of the fluid, okay? So when you say depth, depth is top of the fluid minus y, not the container. I don't care about the container, I care about where's the top of the fluid. So, I ask again, what's the depth? 2 minus y. All right, now the area, again, I beg you, I know a student has no clue if they put base times height divided by 2 for the area. It's not the area of the triangle. It's how much area this slice has. Now, if you're thinking, oh gosh, do I have to do a trapezoid area here? No, you don't. It is so thin that this slant is pretty much a non-issue. It's really just still the area of a line. And so it is still area of a slice is base times height. You with me? Are you with me? Okay, cool. Now what makes this one a little harder is, what about that base? The base is not constant. The base is changing, all right? Wouldn't you agree that the base is going to go to wherever the right endpoint is, which basically makes it the base is a varying horizontal distance, which we call x, okay? X. And what's the height? dy. Now that obviously is a problem because we're integrating with respect to y, but we have x in the problem. What are the limits of integration? 0 to 2. Again, only where the fluid is. Now, this is my next problem. I need to sub in for x. Now let's look at this. I think you'll agree that this point shows an xy relationship. It is the point 9, 4, yeah? And there are many other xy relationships along this line. X relates to y through the line y equals rise over run 4/9 x, yeah? Obviously, again, not drawn to scale. All right, now that's great. Do I use 4/9 x or do I use 9/4 y? Okay, so x is 9/4 y. So 6,600 from 0 to 2 of 2 minus y, 9/4 y, dy. Stop that in your calculator. Trying to help you. Where's my grade book? All right, what do you say? People, somebody?
I got
19,800 newtons. Okay, sounds good. All right, you with me? All right. Let's consider a slightly different case. This is a triangular face, but it's got a little symmetry to it. Trough with an isosceles face, top edge 10, side 4. Wish I would have made this a little cleaner, but it is what it is. Is filled. Yours is different?
Yes, ours says top edge 8 meters and
Oh.
side edge 5.
Oh, good, I did make it easier. Excellent. That'll be much better. Hey. Thank you for speaking up and not letting me get through all the whole problem. All right, cool. Now, find the force the water exerts on the phase it's full. Again, I want you to put the origin at the bottom. You've got to locate your axis in your homework. If you don't have a picture, it will be incomplete. All right, so I need to find, all right, what's the force on this slice? What's the force on this slice? What's the force on this slice? And add them all up. So here we go. The force is, I know it's rho dA, but I still see PdA, which is appropriate with Sadie's coming up, am I right? So what about rho? What is it? 9,800. All right. What is the depth? Now the problem is that this 8 is here, so this side is 4. I don't have the vertical measure. What is the vertical measure? What's this? That's a triple, so it's 3, yeah? Okay, so that's why I changed the numbers to make it prettier. It's 3. Lee? So what is the depth of any slice? 3 minus y. Y is the distance from the origin up to a slice. The distance from the top down to that slice is upper minus lower 3 minus y. Cool? The area of each of these. Area is a rectangle. The base is? The base is? Constant or variable? 1x or 2x? 2x. Now that there's symmetry, there's an x on each side. It's 2x dy. And we will need to sub for x. So what's the xy relationship? 3/4 x. So x is 4/3 y. So the area of the slices, the base is 2x, but in place of x, I'm using 4/3 y. The height of the slices is super thin dy. Limits of integration, 0 to 3. Throw that in your calculator. Lee, what do you get? Talk to me.
117,600.
Okay, are we good? It's getting a little harder. Here we go. Hey, circular face. A barrel full of water is laid on its side. So you're looking at this kind of thing. And it's full of water. That's an important word. Find the force applied to the circular face of the barrel. Always. You want the origin at the center of the circle here. You don't, in this case, you don't want it at the bottom because then you have a shifted circle equation, which is gross. You want the simplest circle equation, and that's with the center at the origin, or center, the origin at the center. Okay, so if force is the sum of many rho dA's, all right, it's water, and therefore the rho is 800. The depth. Now, let's go back and figure our picture out. It says the height of the barrel was 1 meter. That's this before it got tipped. And the radius is 0.5. So here's 0.5, 0.5, negative, negative 0.5, positive 0.5. Cool. And it's filled. So what's the depth of any slice? Upper minus low. What's upper of all these rays? 0.5. What's the lower? Y. So it is 0.5 minus y. Now let's let's make sure this makes sense. I think you'll agree that there's a slice here at negative 0.25, yeah? All right. How deep is it? 0.75. Is this working? 0.5 minus negative 0.25. Does that yield 0.75 deep? It does. Okay. So what about the area of, now again, don't you dare do pi r squared here. Area is base height, because we're talking the area of a slice. And the base, is it constant x or 2x? 2x dy. What is the xy relationship? X squared plus y squared is 0.5 squared. What's 0.5 squared? 0.25. So x is okay, but isn't x plus or minus? Do I have to set the plus or minus?
No.
Why not? Because of the 2. Really, I'm just saying, I'm just going to do the right side and then don't. Follow? Okay, so then the area is 2 root 0.25 minus y squared dy. We from low of to a high of. Throw that in your calculator, please. You could do some ultraviolet booting, or you could use some of it if you really want to. We're not time. This is not going well. But it takes away. Answer? 3,000. 3,000.
I got 848.
848.
We have
0.4. You don't have that? 451.
I got that.
Okay. Are we good? Okay. Now let's think a little bit here. Say that barrel then was, instead of putting on its side, which means it could roll away, you kept it oriented the typical way. So it looks like this. Now, obviously, the force on the bottom is no longer a calculus problem, because that's a horizontal face. We could just do area of pi r squared. The depth is always the same. It would be easy, yeah?
Yeah.
But what about the area or the force applied to the side? Now, let's put our origin here this time. Force is rho dA, 9,800. This one will require you to do a little thinking. You're saying, what's the force of this slice? And what's the force on that slice? And on that slice? So let's do depth is easy. What's the depth? How tall is the barrel? I think it's 1 meter, wasn't it? Yeah. Okay, so how deep is each slice? 1 minus y. That's not the hard part. The hard part is the area. So is it, when I say area, is it the area of this? Or is it the area of this line? Oh, you're good. It's true. So what is the base of the line? Unwrapped, it's a rectangle. What's the base of that rectangle? Right. This distance is this distance, which is 2 pi r. And is r varying or constant? Constantly 0.5. So the base of every one of those slices is pi. What's the height of each of those slices? Y. So the area is pi dy, and the limits 0 to 1. Got that in your calculator? I definitely don't want this shade if that makes it look like I want it. This is probably some ugly decimal by virtue of pi there. What do you got? 2,000? 15,000? 390, 393.804? Okay, cool. All right, that one's a hard case. The other hard case is trapezoids. Okay, so this happens a lot, like when you have a gutter and such. And then there's a flowing water problem we probably won't get to. But if you have a trapezoid case, say the gutter's clogged and filled with water, and so this end of the gutter is feeling the force of the water. How much force is applied to this trapezoidal end? Base 1 is 0.1, base 2 is 0.16, and the height is 0.08, or 8 centimeters, or yeah, 8 centimeters. You with me? Okay, now let's redraw and do this well. You want the origin at the middle of the bottom. Okay, let's talk about each little piece. This is 0.01 all the way across, so this is 0.05 and 0.05 on each side, yay? And this is 0.16 all the way across, so that's 0.08 and 0.08 on each side, oui? And this is 0.08 for the height. Are we done?
Yes.
All right, cool. Picture, definitely taking your time on it helps you do the problem easier later. So force is the sum of many force calculations. It's water, so 9,800, and it's filled. Keep that in mind. So, what's the depth? 0.08 minus y. Do we all agree with that? Okay, cool. The area, draw some slices. The area, is this those circly things, or now is this back to rectangles? Back to rectangles. Is the base constant, x, or 2x? Those are really the three cases. 2x, dy, and now we need another relationship. Now that's what makes this problem difficult. The x relates to the y at any point. How wide it is relates back to how high you are. The higher you up, the bigger the x, yeah? So the x and y relates along this line. So this is going to take a little more skill on it in the algebra putting on your part. What's a point on the slope on that one? This one's probably easiest. Yeah, 0.50, because that's got a 0 in it at least. Yeah. What's the slope? What's the rise? 0.08. Run, be careful. Is the run 0.08 also? This is the run, not this is the run. This is the run. That's the run. So what's the run? 0.03, right? So the slope is 8/3 if we dump the decimal. Cool? So the equation is y equals 8/3 times the sum or difference x minus 0.05. You track it. Now, do I use that or do I solve for x? I have to solve for x. So x is 3hy plus 0.05. All right, now we're ready to go. We said the area is 2x, but in place of x, 3hy plus 0.05 dy. Limits of integration. 0 to 0.08. How much force applied to this gutter face? Seven 3.73. Oh, you're reading digits now. 3.3 newtons? Yes? Okay, 3.763 newtons on his face. All right, that's as ugly as you're going to see, unless you have an inclined plane, which, again, I don't know if we get to. Okay, cool. So you still have, how do I tend to do this well? You still have set 73, yes?
Yes.
Did we get any of the backside looked at? All right. At the very least, let's check some answers to the backside, and I think tomorrow there's no lesson, it's just a big catch-up day. So tomorrow, we're just gonna get all questions answered, right? So at the very least, let's check your answers here. So the easy ones on the back of 72B. And tomorrow, you're gonna come with 3 homeworks. 72B, 73, and 74, right? Okay, and I'll have a lot of fun this weekend grading top load of homework. Hey, are we good to move down? Our road? 1 and 3 are pretty straightforward. 2 and 4 require you to use a derivative rule with the memorized facts. Okay, 7 was a bit hairy in that you had critical numbers at the flex points, but you also had critical numbers where there was a horizontal tangent, so that was pretty gross. I jumped 6. 5, I think, was pretty straightforward. That's a sharp turn, so in your derivative, 1 should not be included, right? But on 6, tangent is smooth at 0, so when you flip it, on f prime, you should include 0 in one of your pieces to the derivative because the derivative does exist at that flex point. So whether you include it in the first or the second is up to you, but you should have it included. And then your derivative should go negative secant squared to positive secant squared. Pretty cool there. All right. Did we get 7 looked at? All right, I'll give you a second to look at 7. I thought that was one of the harder problems. It's just gross. B and D, you had to find the derivative and then find the zeros of the derivative, which was a quadratic. So it wasn't conceptually hard. It's just gross. Yeah. Okay, and then. Maybe get a little bit talked about, at least the easy ones. D was a humdinger, but A, B, and C I think were straightforward. Where did you say a relative min on the curve? Relative min at, where did you say? Negative 1, because f prime goes negative to positive. Easy enough, first derivative test. Okay, what about... that's all we get. Well, let's do B. What about max? Negative 5, relative max at negative 5. All right, we'll finish going over this tomorrow because the first derivative goes positive to negative. So hang on to it, and tomorrow we'll get it all done. Have a great day.